I took a piece of plywood and we cut it to fit where the door was. And we made a hole in the center and mounted a fan that Princess Auto, which is a company that sells a lot of mechanical equipment. And that time, it was selling equipment that was surplus from the war. And they had some fans that were used for cabin pressurization of aircraft. And these are little 28-volt DC motors that ran at 30,000 RPM or something like this, some screaming meanie. And I bought one of these fans, mounted on the center of the door. I made an AC to DC converter, and so I could vary the voltage to this and consequently the speed of the fan. And we had the blower door. And we then do pressure tests on the house.
Welcome to the Flow Lab, the podcast where we dive deep into the science of building performance and HVAC innovations. Today we bring you another insightful episode aimed to enhance your knowledge and expertise in the field. Joining us are your co-hosts, Ben Walker, co-CEO of Retrotec, and Sam Myers, a renowned building science specialist and Retrotec trainer. Together, they bring a wealth of experience and knowledge to ensure our discussions are both informative and engaging. So, sit back, relax, and get ready to enter the Flow Lab, where we'll explore the world of building performance. Let's get started.
Welcome to the Flow Lab podcast. I'm Ben Walker, and this is Sam Myers, and I'm just happy to be bringing this platform to industry and everything. We have recorded a bunch of great episodes already with some really special guests and stuff, and we can't wait to bring it to you guys.
Yeah, so one thing that we're trying to do with the Flow Lab is bring some industry experts in, some people that have been working in building science for a very long time, and just kind of hear some of the stories of how some of these concepts got started, as well as bring in some professionals that are in the field now and talking about some of the projects they have going on. So there's a lot of podcasts out there. A lot of companies have them. We see that there's a gap out there where there's a lot of the stuff going on in building science that's just not being talked about. Building science is a interdisciplinary trade that's made up of all kinds of different professionals and contractors. And there's just lots to talk about to make our buildings better. So thanks for joining us. We're excited. And this is the first episode.
Yeah, I'm super excited about this one. A lot of times people ask about, where did the blower door come from and things like that. And, I don't think anyone really has a super clear answer, but, several years ago, I was at EBA conference in San Diego and just at the trade show booth there. And this older gentleman comes up to me and he just tells me, he's like, I'm the one that invented the blower door. And I'm like, oh, really? I've never met him before, never really heard anything about him before. I'd been in the industry since 1995, but, he introduced himself as Harold Orr and talked about his work at the Passive House there in Saskatchewan. And it's just a great story, and it was an honor to actually have him on the podcast. And I don't think that he does too many of these things anymore and stuff. So it was, I think, a great person to connect with and bring that conversation to you guys.
After really looking into who he is, Harold Orr should be a more recognized name in our industry because we wouldn't be here likely without him. I mean, he really started this whole concept and was the first one to really think about using a fan to measure air tightness to make buildings more efficient and more comfortable. So he was pretty far ahead of his time. He was doing this before there was a Retrotec or an energy conservatory. He was the one that started it. So we're really happy to have him as our first guest to tell that story of how it all began.
Yeah, definitely. And then, I think we need to do maybe a DNA test to see if he's related to Brian Orr.
Something about that name.
Yeah, like that. But that was a great privilege and honor to speak to him. And hopefully we'll just crank up the episode now.
Yeah, enjoy.
Hi, Harold. Are you there?
Hello.
Hey.
Hello.
Yes, I am.
All right.
Good. Yeah. Maybe this will work a little better for us. Thanks for sticking it out with us.
Yeah. Sorry about all the issues.
Okay. What's your question?
Sure. It'd be really interesting just to get a little bit of background on how you started in the air tightness industry, and curious about, the Saskatchewan Conservation House. And it's like, if I can
tongue twister of the day.
Yeah, exactly.
Okay. I started doing carpenter work when I was 12 years old, back in 1943.
Oh, wow.
And my father, we needed a house, and my father decided to build a house. And so I was 12 years old in the summer, and so I started doing carpenter work. And I was doing carpenter work until I got my second-class carpenter's papers. And during this time, I had started engineering and had taken 2 years of mechanical engineering at the University of Saskatchewan, and had dropped out because I was spending too much time on the road between Saskatoon and Regina, with 2.5 hours away, because I was courting my wife. And so I dropped out and did carpenter work. We got married, and I was working for the provincial architect's office at the university, at the province of Saskatchewan. And I was working toward becoming an architect. And the architect I was working under left the government service and left me sitting high and dry. And they hired a new architect to fill his place, and he and I just didn't fit together. And so I decided it was time to do something different. So I applied to the University of Manitoba to get a degree in architecture. And architecture there is a 5-year course, and I was married and had, at this time, 2 children. And I had 2 years of engineering already, and so I could come back and get my degree in 2 years, engineering degree in 2 years. So we moved to Saskatoon, and I started back at taking engineering. And now, instead of being at the bottom of the class, I'm at the top of the class. And so when I was getting ready to graduate, one of the professors, 3 of us aside, and said, "You fellows are the top of the class, and you really need to go on and get a master's degree." And so I started in and started taking a master's degree in 1960. And in 61, I was starting my thesis, and one of the questions we had at the time was calculating the heat loss of buildings. We didn't have a good way of handling how much air leakage there was. And ASHRAE recommended that you take a feeler gauge and measure the cracks around the windows and the doors, and you use this number to calculate the air leakage in the house. And when you did this, you got we had, in our area, our windows were very tight. And so actually when you didn't have a feeler gauge thin enough to stick into the crack, and there really wasn't a crack. And so when you did the calculations, you didn't get anything for air leakage, and we knew that we were having air leakage. And so what did we do? Well, you calculated the heat loss through the walls and the ceiling and the floor and whatever, and then you doubled it and used that to calculate the size of the heating system that you needed. But that really wasn't very good. And so my professor suggested, why don't you do a thesis on an instrument to measure the air leakage in buildings? And so I started my work on, and what we decided to do was to use a tracer gas. And we started in 1961, and the university didn't have the equipment I needed. But there was on the campus an office of the National Research Council, building research, and they had a small research station here in Saskatoon. And so I was using their equipment and I built an instrument to measure how much helium there was in the air. And we would take 100 cubic feet of helium and dump it into the cold air return of the furnace and let the furnace mix it through the house. And then with my instrument, we would try and measure how fast the helium disappeared. I worked on this for a year. And at the end of the year, when I was supposed to be writing my thesis, I could have written, this is what we did, but the stupid thing doesn't work. And that doesn't go very well for a thesis. So the university put me on staff, and I taught a class in thermodynamics for the year and spent all my spare time working on this stupid instrument to measure infiltration in housing. And in 1963, I got my thesis published. And what we were using basically was this instrument which actually measured the thermal conductivity of the air-helium mixture. And as the helium disappeared from the house due to ventilation, the conductivity changed, and so we could measure this. And I wrote the thesis and published it and got my master's degree. Well, as soon as I got my master's degree, the National Research Council put me on staff to continue work on the same thing. And one of the things we did then was to change from using helium as a tracer gas to using sulfur hexafluoride as a tracer gas. And whereas we took 100 cubic feet of helium to do a test on a house, we could do the same test with 1 teaspoonful of sulfur hexafluoride gas. That's 1 teaspoonful. And so that made a major difference in terms of cost. And then we changed the technique that we were using, and we used one of the first computers that were available commercially, an Apple IIe.
Of course,
it allowed us to use this computer to do things. And so we set up a system that would take a sample of the air sulfur hexafluoride mix. We would run it through a gas chromatograph, which would separate the components, oxygen, nitrogen, sulfur hexafluoride, and give us peaks for these. And we could measure then the peaks, the area of the peak, and to know how much of this we had. And so we would select a concentration that we wanted, I think it was 15 parts per billion of this sulfur hexafluoride in the air. And if it was when it's below this peak, as it was being flushed out of the house, we would calculate how much additional sulfur hexafluoride we need to inject. And we made an injector system that would inject a little tiny puffs of sulfur hexafluoride, and we'd pump in enough puffs to bring it up to our 15 parts per billion. And as we did this monitored then the ventilation of the house over a period of time. And it worked very well. The problem was that to do a test like this on a house, we would put the equipment, which weighed about 200 pounds, take it down into the basement of the house, connect it up, run it for a week, and then take it out and then analyze the numbers that we got from this. Well, the equipment in today's number that we're using was about $5 million.
Oh, wow.
And it took a week to do a test on a building, and you just can't do that on every house.
Yeah.
Right.
And so I was aware of George Chmura's work in Ottawa, where he was trying to find out where are the holes in the house. And so what he did was to take a sheet of polyethylene and cover the roof and tape it around the top of the walls of the house. And then he would tape the sheets and cover the windows and cover the doors. And then he would take air from the house he put a piece of plywood in a basement window and took a 12 feet duct out into the backyard, and they put exhaust fan on this to suck air out of the house. And then he used an anemometer to measure the airflow coming through this long duct. And this was a very time-consuming thing because he put the anemometer in various areas of the duct, divide the duct up into 10 equal spaces, and put the anemometer at the center of each of these spaces, and then you get 10 readings, and he'd average this for the airflow and take about an hour, something in the order of an hour to get a reading. And so anyway, I thought that was stupid. And so I took a piece of plywood and we cut it to fit where the door was. And we made a hole in the center and mounted a fan that Princess Auto, which is a company that sells a lot of mechanical equipment. And that time it was selling equipment that was surplus from the war. And they had some fans that were used for cabin pressurization of aircraft. And these are little 28-volt DC motors that ran at 30,000 RPM or something like this, some screaming meanie. And I bought one of these fans, mounted on the center of the door. I made an AC to DC converter, and so I could vary the voltage to this and consequently the speed of the fan. And we had the blower door. And we then do pressure tests on the house. And I wrote my first paper then on this.
The apparatus.
I wrote a paper on this using this blower door. And at that time, I forget the name of the fellow, but he was from Minneapolis, and he read my paper, came up to Saskatoon and saw the equipment that we'd made, and went back to Minneapolis and started the Minneapolis blower door.
Oh, sure, yeah, Gary Nelson, yeah, of course.
Yep.
So anyway, we took the plywood and cut it into 3 equal units horizontally, and put piano hinges on this so we could fold it up into a width of the door and about 30 inches long, a panel that one person could easily pick up and put in the back of the car. And this motor was 9 inches, this fan that we're using was 9 inches in diameter and 9 inches long. And to measure the airflow, we put a smooth edge orifice with a throat of 5 inches in diameter that expanded then to the 9 inches and a nice smooth thing. And that was our measurement system for measuring the air velocity. We had pressure taps around the throat of the nozzle, and these are all connected to one thing, and we put a manometer on there and measured the pressure, and there we had our airflow. And that worked very, very nicely. And I had a request to do a test up near Alaska, up in the Yukon territories. And so I took our unit and checked luggage and flew up to Whitehorse, and we got in the car They didn't have room in the trunk, so we put it on the roof and tied it down as a car. And we drove, it was about 60 miles to where we were going. And we drove there, and it was gone.
Oh, man.
We'd lost it.
No way. Oh, no.
Never did find it.
Oh, no.
Oh, no.
So I went back to Saskatoon, and we contacted the company that made the fans originally for the aircraft, and we bought a couple of them and asked them to wire them for 120 volts, 120 volts. So we just used a variac to adjust the speed and a rectifier bridge to make it into DC. And that worked very, very well.
And back then, did you try for a target differential? Were you still targeting 50 pascals? And do you know where that kind of came from?
Well, of course, back at that time, we were using inches of water and so on.
Of course.
And it was when, I don't know who was responsible for that, but they were suggesting that we should do it in terms of pascals and not inches of water.
Yeah.
And, but anyway, well, while we were involved in this, about the same time, in the early 70s, of course, there was this, the Arabs thought they weren't getting enough money for their crude oil. And so overnight, they doubled the price of oil, which doubled the price of gasoline. And so you went to the service station. Yesterday, you paid 35 cents a gallon for your gasoline, and today it's 70 cents. And so what do? Well, you only put in half a tank because I'd only have half that much money.
Right.
Yeah.
And
it sounds cheap these days.
But our government at that time, the Saskatchewan government at that time, asked they have a research arm called the Saskatchewan Research Council, and it tries to solve problems that are unique to Saskatchewan. But this was one that they asked them to do, was to design and build a solar house appropriate for Saskatchewan. And in Fahrenheit degree days, we're at 11,000 degree days. Quite a chilly place to live, actually. And so the fellow they put in charge of this, Dave Eyre, a scientist, had essentially no expertise in building at all. And so he asked then a number of people in his area to sit on a committee and help them design and build this solar house appropriate for Saskatchewan. And I was asked to sit on the committee. So at our first committee meeting, one of the questions was, well, how much insulation do we put in the walls of the house? And someone suggested, well, why don't we put in R20? Because at that time, R7 was the standard insulation that we were putting in the walls, a 2-inch bat. And they said, that's 3 times that much. Why don't we use R20? And I said, well, I've seen a couple of houses being built with R20, and they're not getting the bang that they're hoping for. And I suggest that we should put in at least R40 in the walls and R60 in the ceiling. And we don't build a basement. We put it in a crawl space, and we insulate the floor very well. And so that's, in fact, what we did. We built this Saskatchewan Conservation House, and they put a thermal collector for collecting solar energy and a 2,000-gallon water tank to store the hot water, or 20,000-gallon water tank to store the hot water. And we insulated it with R100. And we built the house, and it worked very well, except that the maintenance cost for it for the first year was $10,000. And the second year they had it, the maintenance cost was $5,000. And they sold the house the third year, and the new owner took the system off.
Oh, wow.
Oh, man.
So, but anyway.
And is it true that that house had an air change of 0.5 air changes per hour?
That's right.
Yeah.
When it came to air changes, and I had to have a carpenter's license, and when it came to coming to put the vapor barrier in, I made the point that I would put the vapor barrier on. And so I took one of our technicians that I was working with at our office, and he and I went down to Regina and installed the vapor barrier. And we were very careful to do this, using acoustical sealant to seal the joints between the vapor barrier, one sheet of vapor barrier and the other. And we were very conscientious in doing this. So when we did a blower door test, it was half an air change, 0.5 at 50 pascals. And as a result of that, when, what's his name? I forgot his name now. Dr. Fest, anyway, from Germany, came over and saw what we'd done, that they went back and started the passive house movement in Europe, where that if you build or renovate a building, you shall bring it to the passive house standard, and they require 0.6 air changes per hour at 50 pascals.
Yeah.
Not quite as good as we did, but
pretty decent still.
much better than normally done. Now,
what were you using for a vapor barrier back then?
Well, we were using on the Saskatchewan Conservation House. We used 6 mil poly.
Okay.
But before that, we were using 2 mil poly. But I think everybody now is using 6 mil poly here.
Gotcha.
But the problem I have is that, and where are the leaks in the house? And my estimation is that they are likely in the ceiling.
Yeah.
And why is that? Well, and take, for example, my house. I have a 1,100 square foot bungalow with a full basement. And the ceiling now, well, the interior partitions, I have 160 lineal feet of interior partitions. There's 2 sides to that because the poly joins to the partitions on each side. So there's 320 feet of ceiling that you have to seal the poly to, plus the outside wall, which is 140 feet. You add 320 and 400 and 140, that's 460 lineal feet of crack. And unless this is sealed, unfortunately, when they put the drywall on the walls and on the ceiling, they do not screw it to the top plate, and they do not fasten the ceiling close to the walls. And why do they do that? Well, because when they tape the joint there, they want a little flexibility, so as the house moves a little bit, it doesn't crack, break the tape on the joints. And so they put the screws back away from the corners about a foot. And this means that there's nothing then to hold the edges of the poly behind this to make it seal. And in order to make it seal, you have to use something between the sheets of poly. And here in Canada, we are required to place over top of the partition or between the top plates of the partition a piece of poly that's about a foot wide that hangs down on either side of the partition. And then you put the poly on the ceiling and join it to this. But that is never airtight unless you put something sealant in there. And the only thing that we really found that was effective in doing this was acoustical sealant. If you use a caulking compound, the caulking compound is when it hardens, does not seal to the poly. But acoustical sealant is designed to stay sticky.
Yeah.
I guess would be a good word. And you put acoustical sealant on, and then when you put the next poly on, the acoustical sealant acts as a glue to join the two sheets of poly together. But in terms of building, we've designed a better way of doing it, and that is that if you, what we call the prairie double wall house. With the prairie double wall, we build the outside wall of the house as a 2x4 wall with insulation, just as it was normally built in building a house. But then, while it's still on the floor as you're building it, we put a vapor barrier on the outside of the inside wall. We place sheathing on top of it, and we extend the vapor barrier so it extends past the top plates and the bottom plates and the studs. And then we put sheathing on it, and then we build the outside wall right on top of this, and then lift it up to make the space for the insulation between the two walls. And we build the second wall on top of the inside wall. And when it got it lifted up in the proper place, we nail a strip of plywood or OSB along the top plates and the bottom plates, and around the window openings and around the door openings. And so we have to make the windows and door openings just a little bit larger for this, about 3/4 of an inch. And then we insulate between the two walls, and then insulate the outer wall, and then put sheathing on it. And then we stand the wall up. But because we've placed this sheet of plywood under to hold the two walls in their position, the wall is 3/4 of an inch taller than normal. So when we get the outside walls up, you can place the roof trusses on the house, on the building, without any interior partitions. And then you can put vapor barrier and drywall on the ceiling of the house as large sheets. In fact, as I've watched men doing this, and whereas if you're taking a couple of men and putting the drywall on the interior of a house, it's normally it's a 1 or 2 day job just putting it on the ceiling, because you've got this little piece here and little piece there, another piece in this closet and another piece in that, and so on. And when you get finished, you got a half-ton truck of drywall scrap that
Right.
you have finished. Whereas if you don't do that, if you do it the other way,
It's like a continuous layer, really.
have no interior partitions, you can start at one corner with a 14-foot sheet of drywall. When you get to the end, you cut the piece off and start the next row with that piece. And when you get finished, you pick up the scrap of drywall from in one hand and throw it in the garbage. And you put the vapor barrier on the ceiling, which consists of one big sheet that covers the whole house if you can buy a sheet that size, or maybe 2 sheets if you can't. So you only have one joint to seal instead of 400 feet of joint to seal. And that makes a major difference in terms of tightness. And a builder that I know of was routinely building houses that with a blower door test of less than 0.1 air change per hour.
Oh, wow.
And routinely doing this. So it makes a major difference, but you have to seal the joints between the individual sheets of poly that you put on the house.
Yeah.
The other thing, of course, on this double wall, if we put the vapor barrier on the outside of the inside wall, we don't have any problems with electrical or plumbing or anything in the inside wall because the vapor barrier is outside of that.
Yeah. Less holes getting poked through it.
Right. So it really makes a difference.
Yeah, I think that's
Anyway.
a common theme still today is just trying to put that air barrier on the outside, just for that same reason. You just have fewer holes, easier to seal, easier to control for. Yeah, that's cool.
Well, give you another story. We have a young couple here in Saskatoon that got married, and one of the first things they did was to buy a house. Now, the house was built originally in the 1950s with R12 in the walls and a poor vapor barrier and whatever. And so the first thing that they did after moving into the house was they got a blower and somebody with insulation. They blew 6 inches of cellulose up in the attic. Well, that cuts the heat from the ceiling a bit. And the second thing they did was they changed the furnace from a 80% furnace to a 96% furnace. Now, the 96% furnace has a fresh air intake from the outside that runs through a 2-inch diameter duct to the furnace, runs through the burner chamber, which is sealed, and then the exhaust gases are ducted out through another 2-inch to the outside, and they don't use the chimney. And so the contractor doing this said to him, he said, "You got to do something about your hot water heater." And he said, "Well, why?" Well, he said, "There's not enough heat from the water heater to make the chimney work." So he said, "What do you suggest?" And he said, "Well, I'd suggest you put in a direct vent water heater." So they did. And in about March of that, following that, he called me up and said, "Would you come and look at my house?" And I went over and we looked up in the attic. There's about 2 inches of frost that completely covered the inside of the roof underneath in the attic. And I said, "Well, that's going to melt as soon as it warms up and fall down and wet your cellulose insulation." And the problem just isn't this year, it's next year and 5 years from now and 10 years from now. And about 10 years from now, you're going to have to tear your roof off and redo the whole thing. And so he said, "What do you suggest?" And I said, "Well, I would suggest a chainsaw retrofit." And
I was going to ask you about that. Yeah. What is that?
What is that? And I said, "Well, you take a chainsaw and you cut your eaves and you overhang off. So you have a nice, neat, rectangular box. And then you wrap this box in polyethylene on the outside, sealing all the joints to make it airtight. And then you strap it to make space for insulation. You put R40 on the outside, and then you put new windows and doors in, and you have a house." So he's a member of our church, and we got a group of young men together, and we started Friday evening. We went over and we took the shingles off the roof, and we got a chainsaw, and we cut the eaves and the overhang off, and we covered the cut ends of this with a sheathing material. So it's completely covered. And then we started in and wrapped the roof of the house down and hanging it down the walls. And then on the next day, we took 2x8s and put them on edge. So on the edge of the roof, the peak of the roof, and 2 more in between. So we have a 9.5-inch space where these are. Then on top of that, we put new 2x4 rafters at 2 foot on center. And this gave us then the 9.5 inches of the 2x10s plus 3.5 inches in the 2x4s for insulation. We put R40 insulation in there, and then over the summer they took the siding off the house and they nailed 2x4s to the side of the rafters to hang down to make the same space that they have on the roof from the walls. So this outer wall then gave them space then for another 40 on the outside. So they wrapped the walls of the house. Actually, they got a backhoe and dug down to the footings, and they wrapped the foundation first with poly, and then they fastened on the concrete wall 2x6s that were laid horizontally, and one about 3.5 inches above the footings, and then the next one up above that was the width of 2 16-inch bats, so about 28 inches apart. And then a third one above that, again, 28 inches apart. And then they put our 20 bats, 2 R20 bats between these horizontals. And they made then panels 8 feet by 8 feet with PWF pressure treated wood and 2x6s, and filled these with R20 insulation, covered it with a 1/2-inch plywood with PWF plywood, and then waterproofed these panels and dropped them in, and the edge of them just sat on the edge of the footing and backfilled against these to hold these in place. And so you had R20 in these panels, R20 in the horizontals, so that gives you R40 on the outside of the foundation. And then we stood these 2x4s on top of this and nailed them to the side of the rafters to make the space above that so we could put R40 in there. And the result is I carefully looked at their energy bills, and they've reduced their energy bills from about $970 a year to their now cost of heating their house for the year. Just the energy for the furnace is $70 a year.
Wow. Yeah, that's the first time I've heard of a chainsaw retrofit.
Yeah.
So I guess the goal of cutting off those overhangs is just to give you a place to, I guess, air seal those top plates and then bring that insulation so it's continuous across the top plate.
That's right. Yeah.
Yeah.
Yeah, just accessibility.
Yeah.
No.
Then just for the viewer then, or the listener, what
one of the concerns was that here we had he put there was about, I think, about R15, R16 insulation, and originally he put another 20, 25 on top of it. So you had about already insulation in the ceiling was about around R30. And is he going to get condensation on his vapor barrier in the attic? And I didn't think he would, but we wanted to make sure about that. So what I did was to buy him an indoor-outdoor thermometer. And we put the outdoor sensor up in the attic. And this records the temperature, makes sure that it records the low point of temperature. And he can watch it, and it never gets low enough for condensation to occur.
Wow. Yeah, it's an easy way to do it without having to, dig into it. You can just calculate that dew point if you have those inputs.
Right. Yeah. So anyway, that's the story. So here I am now. I started all this in 1961. And unfortunately, we still don't have a requirement here in Canada for building to any particular air tightness, but they do in Europe.
Yeah.
And I was over there for a conference, and somebody with a motorcycle, and had a blower door tied on the back of the motorcycle.
Why do you think there is so much pushback to that, Harold? I mean, we struggle with that in the States too. Like our building code here is determined by state, and some states have figured it out and provided a requirement, while others, like the one that I'm in, have not. So still to this day, you would think that we would have, kind of learned the lesson. But what do you think some of the biggest challenges are there?
Well, of course, I think the people doing the legislation are very reticent to say, this is what you have to do. And yet, in some respects, they are doing that. For example, now they are requiring that you have at least R20 and R value in your walls. But they still haven't got to the point of saying you shall build a house that has an air tightness better than 0.6 air changes per hour.
Yeah, it's a tough challenge that we continue to face. There's still the argument that a lot of builders out there that I've talked to believe that a house needs to breathe. That's still a common saying that we hear. What's your response whenever you hear that?
Oh, that's easy. Because yes, your car is built airtight. If it isn't built airtight and you have a crack that allows cold air to come in, you take it back to the dealer and get them to fix it. There's no question about that. Well, how do you get along in an airtight car all the time? Well, it's easy. They bring fresh air in, run it through a heater or a cooler, and put it in the compartment of the car. What's wrong with that? Why can't we do this with houses? Well, it's another $1,500 or $2,000. But what's $2,000 on a $100,000 house, or $200,000, or $300,000 house?
Right.
Yeah. It's just one of the additions that you need to do.
Yeah, I read that for the Saskatchewan Conservation House, you guys installed an HRV. Was that retroactively, or were you guys already thinking about the whole house ventilation while you were doing it?
It was. We knew that we needed to do this, and so one of the technicians at the university, who we had, undertook to build an air-to-air heat exchanger, and in fact, after he had built this, he then started to do this and make air-to-air heat exchangers for animal barns, pigs and chickens and what have you, because that's one of the big problems in terms of farm buildings. And so his name was Dick Van E, and he built the first air-to-air heat exchanger for the Saskatchewan Conservation House. And what he did was he used strips of half-inch plywood to make spacers, and he would lay a strip down the side and then put a layer of polyethylene on. Then he put another half-inch strip and another layer. And between these adjacent layers, the air went from the warm air, it went into the top and down 8 feet and out at the bottom. And the cold air came in at the bottom and up 8 feet and came in at the top through adjacent space. And the heat transfer medium was just 6 mil poly. And he built this, and put an inlet fan and an exhaust fan on it, and it worked very nicely.
Wow.
And then he started building air-to-air heat exchangers for animal barns, and then has been building these for houses as well.
Yeah, that's interesting.
So,
that's
other
a common. I was just going to comment that that's still a challenge too. It's like for, a lot of the areas that are starting to require an air tightness number, the idea of bringing in forced outside air to the inside in the summer and the winter, just some people just can't wrap their heads around it. It's like, why would I want to do that? Like, that's just going to hurt my heating and cooling load, but it really doesn't all that much for a tight envelope, and you're just bringing in a little bit and exhaling a little bit. So yeah, in North Carolina, we have an option, an above code option where air tightness is required, but there's no requirement for ventilation. And then people complain that it doesn't work. So that's just another one of those educational thresholds that we continue to battle with.
Yes. And, well, I don't know that it's required in cars, but the cars manufacturers have realized this is necessary. So why don't we should realize this is necessary for houses too.
Exactly.
Why not?
Yeah, I feel like that's a common theme here. It's like our cars just get so much more design attention than our houses do, and we just spend so much less time in them.
Okay. So are you people are involved in blower doors, are you?
We are. We're a manufacturer.
You manufacture the blowers.
Mm-hmm. Yeah. Digital pressure gauges and blower door systems. Yeah, and the software and everything. So it's great to have like the kind of the story, your story, the origin of the blower door and kind of where it started is, one of the things that for our podcast we were kind of really trying to dive into and kind of figure out, really where it kind of started from. And it seems like that you were more likely involved in developing the first one.
Yes.
That's yeah.
Yeah, it's cool to hear that history of it. I mean, we have customers that are in a variety of different industries. We have home builders that are starting to do this more. They're using blower doors as like a quality control as they continue the build. We have HVAC contractors that are starting to use them to see if a comfort problem is actually an HVAC thing or if it's just a problem with the house itself. And then insulators are starting to do it now too. They'll do a pre-test and then they'll test again at the end to kind of have the papers to prove that their air sealing did work and it brought that air leakage number down. But and of course, energy auditors are using these also. So we're starting to see that more and more trades are starting to pay attention to this more.
Right. Yeah. Anyway, I spent 3 years down in Oklahoma City teaching engineering at Oklahoma Christian College. And we were living in a house down there and I'd figured out that it has almost exactly the same cubic footage of space as our house here in Saskatoon. Now, Oklahoma City,
in different climate,
is quite a different climate from Saskatoon. And I was surprised to find that the house down in Oklahoma used almost exactly the same amount of fuel to heat it over the winter as it does in Saskatoon.
Oh, wow.
Wow.
And my house here in Saskatoon was built before any of these. It was built in 1960. And before any of these things got started, the result was when I was having the house built, Owens Corning had just come out with a brand new insulation, which they called the full thick bat. And I asked the contractor, I said, you want you to use that full thick bat in the walls of the house? And he said, oh, don't do that. He said, it was like never pay for it.
Oh, yeah.
So I said, well, you tell me how much extra it costs and let me make the decision of whether you put it in or not. And he said, he did the calculations and it cost me $25 extra to have the full thick bat.
Seems like it makes sense.
Well,
Yeah.
I think I saved over $25 the first year, and I think now it's saving me something in the order of about $400 a year.
Yeah.
So it's
well worth it.
Best investment I ever made.
Yeah, I'm a little envious of some of the builders in Canada, because you guys can have a vapor barrier because you're heating only, and then when you get down south to where we heat and cool, we have to have a vapor retarder, because we have to allow moisture to drive in both directions depending on what time of the year it is. And
right,
yeah, we're kind of like the redheaded stepchild down here, because we have all four seasons and we have humidity, and we still have issues to where mechanical systems are getting oversized. We still have new houses that aren't very tight, and the humidity just is pretty relentless. So yeah, it's an ongoing conversation down here for sure about like the best way to do things, especially with the variety of materials that are on the market now.
right, yeah.
Yeah, you'd think we'd have it all figured out by now. But
Yeah.
no, we really appreciate your time today, Harold.
Yeah.
It's an
Okay.
honor to have you on here, and a privilege to be able to talk to you and everything. Really appreciate it.
Hearing the story of that first blower door and how it came about and where the components came from is just really cool to hear.
It is, exactly.
Yeah. Okay. You both have my phone numbers?
We do.
Yeah, definitely.
Let me give you my phone number. It's area code 306-370-2961.
Yeah,
And
perfect.
if you need any help or any concern or anything, don't hesitate to give me a call.
We really appreciate that.
That's excellent. We appreciate it. We may follow up with some questions, as we get going, and have some more, questions about the history of all this, because our lives revolve around it, and those are the kind of questions we get from our customers. So yeah, we appreciate it.
Okay.
All right, awesome.
Okay.
Yeah, thank you, Harold. Appreciate
Thanks
it.
again,
Have a
Harold.
great day. Bye now.